Exploring digital libraries of scientific articles is an essential task to the research community, in both academia and industry. Traditional mechanisms display stored information without almost visual resources. They present briefly textual information by article, in a list-based layout that does not allow exploratory operations, as clustering, filtering, or aggregating, on the results delivered by the digital library. Consider the case where the analyst has a referenced article and wants to look for related works. Except for the articles which share citations or common keywords, the retrieved results will be limited to those which fulfill a syntactic match. If instead of having an article as a reference, the user has an image, the process of finding and explore articles with similar content becomes almost impossible. We propose a two-step method for exploring and analyze scientific document collections by combining image and textual information extracted from articles. Our method relies on the interaction between a content-based image retrieval (CBIR) widget and an interactive multidimensional projection method for mapping similarity relations in 2D space. We exploit other visual resources for representing author and topic information articles according to the selections and preferences of the user. Moreover, a user exploration log is stored for comparing two or more timestamps during the information extraction process, allowing to discover patterns and relations hidden. Multi-CBIR view allows us to input up to 5 images and then obtain a similarity-based ordered list of images by each query. The similarity can be defined from a distance measure between feature vectors. Each query is represented by a different color in the multidimensional projection view. This component maps all the papers of the dataset. Textual information from each document gives rise to a high-dimensional vector that represents the document. Control points are mapped with its respective color of query, and green points correspond to the rest of papers. Linked items. Through hovering over an image or point, Drift will highlight a document and its contained images displayed among components. List-based selection refinement view shows the list of selected documents, depicting the title and DOI. Selection content summarization view. Drift shows a histogram with the most cited authors, a word cloud with information of paper's content, and its year publication histogram. Selection Inspector View represents selections made by the analyst. Each selection is composed of the number of images, documents, and authors. They are displayed with their respective color of layers. User interaction with control points. The analyst can move the control points based on the analysis obtained with the other components. Then, make a selection and add it to the Selection Visual Manager. Choosing A and B states makes it possible to compare them for filtering. State Manager View. This view displays titles, authors, and images. Besides, it adds the option to select the most important documents for the analyst. Finally, a more filtered state containing pertinent items could be generated. The effectiveness of our approach is shown by performing 2 case studies and a user evaluation, which attest to its usefulness for dealing with large scientific articles collections. Case study. This case study analyzes a dataset containing 1369 documents by querying 5 different topics. In this case, we chose 2 images from articles associated with supernovae and gravity. We decided to retrieve a subset of 6 and 9 images displayed next to our input. Its respective documents are located as control points and the rest of the documents are mapped according to its textual proximity. A list of the selected documents is displayed, with a histogram of publications of the authors, a word cloud, and a histogram with the years of the publications. At first, the 2 selections were only control points. The following are selections around them. The below component allows us to start filtering through the titles. With the projection, we can determine the central points have less proximity to the search objective. And it is possible to check it quickly with the word cloud. Then we discern the most important control points based on the previous selections. Now a new selection is made around the filtered control points. The last two created states of the stacked graph are chosen and compared through the Managing State window. To continue filtering, the fourth is selected as State A and the fifth as State B. This component helps to discover which articles match the search. The operations applied are intersection and difference. We choose the articles whose titles seem to be relevant to the search. Based on the filters of the operations between articles, it is possible to create a new state in the stacked graph. In the seventh state, we decide to alter our projection locally, so change our parameter alpha equal to 0.3 to 0.001. Additionally, we reposition two control points. Then we select around these control points. And we filter again at the bottom. Because of this selection contains topics related to our search and various topics, we chose to compare this state with the previous one. In fact, we will compare two states that resulted from different filters. In this case, selections A and B have no articles in common. We continue choosing articles of interest. Next, the Export button lists the titles. Using this option, our prototype generates a file with the data in JSON format. Thus, we can save a customized subset of documents for supporting writing or reading scientific literature tasks. The user evaluation followed these steps: introduction, tool exposure, user familiarization, and evaluation. We perform our evaluation on DT3 dataset. This evaluation was conducted to assess whether drift enables the discovery of documents of interest plausible time in comparison with the list-based paradigm. We invited 6 researchers, all experienced in literature systematic review. We split the participants into 2 groups. Group 1 performs the first activity using drift, and Group 2 using the list-based paradigm. And later the second activity inversely. We set up 2 search activities, A1 and A2, by using 2 specific questions. To evaluate the relevance of document retrieved, we computed precision, recall, and F1 score measures. Here, one observes that in A1, users of the list-based interface obtained a significantly lower performance in terms of all measures. And in A2 activity, Group 1 precision average was decreased while Group 2 was increased considerably. For instance, the user 4, who obtained the poorest precision in A1, improves its performance obtaining 0.75 of precision in A2. Elapsed time per activity. In Figure 8a, we notice that all times list-based users spent almost the same to perform this task. In Figure 8b, one can rapidly notice that drift users obtained the 3 lowest times for this activity. Based on our evaluation, we confirm our initial hypothesis. Users of Drift will spend less time answering questions that require a global analysis of the corpus, with no significant loss in precision.